So you guys got to hear about the hardware side. So I'm going to tell you guys a little bit about the software side. Talks away. Introduction to Robot Operating System, or ROS, which ROS is the robot operating system. And I'm going to talk a little bit about ROS and a little bit about hardware. So I'm the dev advocate for an organization called Open Robotics. And Open Robotics, we basically create open software and hardware platforms for robotics. We use these platforms to solve problems, and we also help others solve their problems with our software. So we're basically the stewards of two large open source projects that you may have heard of. One's called ROS, or Robot Operating System, and the other one's called Gazebo. You may also hear it called Ignition. And Gazebo is a robot simulator. And basically what we're working on and what we're working towards is having a world where you can write a robot and you can simulate a robot and you can move the code between the simulation and the real world, and generally things run as they should. Along with this, we also build all of the tools and things you might need to make a robot run and understand it and build it in a way that's quick and easy and understandable. So we build tools to do not just simulation, but visualization of the robot as it's running, so you can see what it's seeing and kind of tap into its brain. Tools so you can start that robot up and basically configure your Linux environment so it just runs. We have a bunch of tools so you can take a look at the data you've gathered and sort of analyze it, understand how things failed or how things went right. And then there's just also tools to understand how your robot's constructed and put your robot together, and tools to basically build packages and distribute them. So if you're a hardware vendor, you can create a hardware package and everyone can use it right away. So we've been working on this for a long, long time. ROS is not a new thing. It's actually came out initially out of Willow Garage, and it's moved over to Open Robotics. First version, I believe, was actually in 2008, 9? That might be incorrect. We're actually on the last release of ROS 1, which is Noetic. A couple months ago, we released Melodic. And we're actually working on a new version of ROS called ROS 2, which fixes all the things that people complained about in ROS 1 and really gets ROS ready for the prime time, for all of the autonomous vehicles, for these factory operations, for farming operations, all these things that you've been hearing about all day. As of last week, we just released the 5th version of ROS 2, which is Eloquent Illusaur. Illusaur is this crazy turtle from Australia that has a bunch of seaweed growing on its head often. If you're interested in ROS, you can go and check this out right away. It's ready to go. If you're not familiar with ROS and you're sort of skeptical of open source, it usually helps to have some social proof of what you're doing and why it's important. So just in that last presentation, I saw a ton of companies that use ROS. Here's a couple that I pulled out just from September. We had a really good month in September. Embark, which is an autonomous trucking company. It's a startup here in San Francisco, raised $70 million as a Series B. Simbi Robotics, which does this sort of retail establishment checking, looking to make things that are stocked, doing inventory control and that sort of stuff, raised $26 million in a Series A. FarmWise, who's in that farming vertical, raised $14.5 million. Built, which basically automates industrial equipment, or industrial and sort of construction equipment, raised $33 million in a Series B. And then in that same month, Six River Systems was sold for $450 million. So in September alone, you're looking at well over $500 million of money poured into robotics and robotics companies that use ROS. Along with those startups that everyone's interested in, there's a whole bunch of companies that are either like longstanding industrial companies or vehicle manufacturers or universities or established software companies that also use ROS for their R&D projects. So why ROS? What do you get from ROS as a developer? So I like to think of ROS as a tool that you use so you can focus on delivering value in a robotic system and not reinventing the wheel and not rebuilding infrastructure. We've been doing robotics way too long to keep doing the same things over and over and over again. The analogy I often use for people coming from the software space is to say that like ROS is to robot development what Node or Rails might be to web development. And I think we've reached that sort of level of maturity at this point too. And basically ROS is a collection of tried and true robot software patterns that we find are useful for every robot that you're going to create. It's also a set of CLI tools for deployment, monitoring, debugging, and the simulation tools that allow you to sort of build things before you build them and test hypotheses before you spend the money to go and actually build hardware. Furthermore, and I think this is one of the more useful things, is that it's a library of hardware interfaces. So things that you can go buy off the shelf, like cameras and Velodynes and motor drivers, a lot of them already have interfaces to ROS. And probably the thing that's underrated or less talked about, but is probably the most important, is that you have a community of people who all use this tool that come with this knowledge ready to go. So let's talk about what a robot is. If you ask somebody in the robot, like in the 60s, what is a robot? It's this thing with a square head that every cartoon robot has. If you ask somebody from the 80s, it was sort of these 4, 5, 6-axis arms that sort of enabled us to transition from manual labor in manufacturing to something a little bit more automated. If you ask somebody now, it's always this poor robot getting whacked and doing backflips. And more likely, it's the robot sitting in your house cleaning your floors, which has made, I think, everyone's life a little bit more easy. Also, since this is an IoT conference, I think this is actually how the robot revolution is going to take over. It's going to be everyone's toaster oven burning down their house. All right, so what is a robot? I use a really, really loose definition of robot because I actually think it helps people think about ROS as a tool to solve their problems. So I always call a robot as the combination of sensors plus actuators plus control. So sensor is going to be a camera, a depth sensor, something simple like a button or a switch. It might be wheel encoders, it might be GPS, it might be inertial measurement units, it could be any of those things. Actuators can be anything from a very complex, very expensive 6-axis arm to wheels, wings, rotors, servos, basically anything that moves. And then control is usually the thing that somebody's paying you to figure out, right? It's like, how do we take some input, think about it, and make some output happen in the real world? So what is ROS, and how does ROS help you put robots together from these sort of primitives of sensors, actuators, and control? At the heart of it, and probably the biggest and most important piece for ROS, is a pub/sub bus. So if you've used something like RabbitMQ or ZeroMQ or another message passing strategy, you'll find ROS very, very familiar. It's just a message passing system that's tailored for robotics. And we take these topics or these messaging bus and we organize them as topics, which are effectively namespaces. So you can say well, here's all my motors, here's all of the sensors that are cameras, here's the color version of this camera, here's the color version of this camera that is dewarped. Generally speaking, what you'll do is you'll have a bunch of sensors publishing data to topics on this bus, and you'll have a bunch of actuators subscribe to topics on a bus. They may also publish their state. So if an actuator is a little encoder, it might say, I'm at this position, this position, this position, and then you might tell it to go to another position. I'll talk a little bit about ROS2 here. Generally, most ROS1 and ROS2, there's a lot of commonality. ROS2 differs in the sense that in ROS1, we sort of built this pub/sub system from scratch. In ROS2, we've actually worked with a bunch of standards bodies to use what's called a DDS, a data distribution system, to be the backbone of the ROS pub/sub bus. And what this has allowed us to do is clean up a lot of security issues, work on quality of service, because that always was an issue before, and just sort of make sure that things run a lot more reliably and smoothly. Another thing that you need to know about ROS is generally most of your processing happens in a ROS node, which you can think of it as just a really simple either Python program or a C program or a C++ program that's running, and it's just taking this input, processing it, and doing something with the output. So people like to talk about, I'll call them stupid robots. I think you guys have seen this. People may use another S word, but very, very simple robots. And I think that's a great way of thinking about learning ROS and what it can do and what's going on. So I have the most trivial example of parts I had sitting on my desk, basically. So there's an ultrasonic sensor, which is basically a distance sensor. right? And then I had a little stepper motor sitting on my desk, right? And so why don't we build something where we just take a piece of tape, we put it on the end of the stepper motor, and then we grab a ping pong ball, and what we want is a really, really stupid robot that if you throw a ping pong ball at the sensor, the stepper will basically bat it out of the way. So how would you build this? Like, a lot of people will just go and like, oh, I can just do this all in Arduino, I have to write all this code. ROS makes it really, really easy, and I'll show you sort of progressively how things get easier and easier and easier. So if we were to do this all from scratch in ROS, all from scratch, we would start with the sensor. And the sensor is really simple. We'd create a ROS node, and the ROS node, let's say, would publish to something called sensor/distance, and there'd be a distance message. And it'd be something like, oh, it'd start at infinitely far away, and it'd get progressively closer, closer, closer to 0. So you take your hand, you set it back here, it'd be at like 1 million, get closer, 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 you put your hand on the thing, it'd say 0. And this thing would just publish, and let's say it'd publish at like 100 hertz or 200 hertz. Similarly, we'd have the actuator, and we're going to call this thing the slapper. And the slapper is going to basically, it's going to listen on a topic called slapper. It's going to listen for something like, hey, start slapping. And it's also probably going to publish, usually what you have is just publishing its state. So it's either going to publish its position from like 360 to 0, or it's going to say, I'm running, I'm not running. Doesn't really matter. You pick one. So to make a robot work, we just create a third ROS node that would basically be our control system. And it would subscribe to the sensor, and it'd say, oh, what's the distance? And it would publish to the slapper thing that would turn the slapper on or off. And all we would have to write is just, it's a big while loop because it's always running, our robot's always going. And it'd say, hey, check the sensor. If the sensor distance is less than some arbitrary value, make the thing slap, otherwise make it stop. And that's really all that would be involved in this robot. And this is actually more work than you'd have to do with ROS, most likely. So ROS is this, one of the biggest parts of it, and one of the more useful parts of it is it's a sort of federated build system. So in the past few years, software has been more focused on these sort of large, monolithic pieces of code. Well, we don't do that because we're sort of an open source organization, and we're working with lots of different people in lots of different places. So we have lots of different repositories. Some of them are C++, some of them are Python, some of them are even Java, which is rough, but you know, it happens. So there's all these packages, and ROS has a build system that basically allows you to write in whatever language you want. ROS will find that package, pull down latest versions, compile them, and build an executable file that you can run. And very often, what you can do is not build all of your packages from scratch. You can actually just pull them down from somewhere else. So if you're building this, there more than likely the case is that you could probably go and find a package for this sensor. You know, and it's written by like some graduate student. It's C++. It was written 20 years ago, but it still works and it's great. And then somebody else came through and wrote a package, maybe a Python package for the stepper. So you're really not even writing these two bits of the robot. You can kind of just go and pull them down and build them. And there's a lot of these. There are tons of these. I don't have the exact number, but I think it's we're in the tens of thousands range of packages. So it's everything that I've already talked about. It's the sensors, it's the cameras, it's the drivers for different motors. It's all sorts of different tools for building robots. And most of them are listed here. All right, so we got our robot. It's basically ready to go. We built the control. We pulled down packages to implement the sensors and the actuators. ROS has even more stuff that helps us out. So we have in ROS, we have what's called a launch file. A launch file is basically a bunch of system administration tools that allow you to take all of those packages that you've built into executables. You can take all those executables and string them together and start them at the same time in their own process. So you don't have to write that. That's already done. You don't have to think about that. You don't have to do any of the shell scripting or anything like this if you had to write all this code from scratch. So your robot's sort of functional now. You can start it, you can run it, you can do all these things. But more than likely not, if you're any sort of normal software developer, you don't get things right on the first try. So ROS also offers a lot of tools for debugging and testing your code. And probably the most powerful of these tools is what's called a ROS bag. So what a ROS bag is basically you can take anything on that messaging bus, anything on that pub sub bus, anything running at 1,000 hertz or 100 hertz or 1 hertz, and you can save it to a file and you can replay it and you can parse that file and you can do all sorts of stuff with it. And this is super, super powerful because what you can do is you can basically, like if you have a complex robot, you can actually find a behavior that you don't like. Say you have some sort of moving robot that does something, it falls over, it runs into a chair. You can actually capture that behavior, log it, and then you can actually build a test around it. And I think this is actually fundamentally the most powerful part of ROS because you can also do stuff like, hey, I have a bunch of sensors, I have my robot, I'm going to go do something complex like take it out to the ocean, which is probably really expensive, and I'm going to go run my autonomous drone in the ocean, and I'm going to get all this data. And you can save it, and then you can send it to somebody on the other side of the globe to process it and understand it. ROS also has a lot of other really sophisticated tools for building much more complex robots. As I've said before, we have Gazebo and Ignition, which are these simulation tools that allow you to basically build a robot in simulation and have all its behaviors run in simulation without having the physical robot present. We also have a tool called RViz. And what RViz allows you to do, so say you have one of these autonomous vehicles driving around, RViz will allow you to pick any of the cameras on there, any of the LiDAR systems, and see what's going on with them and see them in the frame of reference of the robot itself. If you're doing any sort of mapping, you can overlay those maps and see how things are going and see where the robot thinks it is in terms of that map. We also have a set of tools called our Qt Suite, which allows you to sort of pick and choose from all these parts in RViz and build up little tiny apps on top of it. So over and above all of this, ROS has tools for what I call doing the hard math. So I have a background in robotics, but there's a lot of hard math associated with making things move. ROS comes with a set of tools called TF, which basically tells you the position of anything in your robot with respect to anything else and allows you to change those coordinate frames between all these different parts. And this basically abstracts away that very, very complex part of building a robot that usually you go to grad school to learn. There's another tool for this hard math that's called Move It. And so what Move It allows you to do is, I don't know if you've ever played with a 5-axis arm, one of these robot arms that you might find in a factory. You can make it do all sorts of dangerous things, right? You can make it hit itself. You can make it get into a position where it can't turn around correctly. You can make it run into a person and hurt them. And so what Move It is it basically does what's called inverse kinematics. It lets you say, I want to take this arm from here to here without doing any of those things. And there's a solver that allows you to do that. And so that's one of those tools that's just baked into ROS that you don't have to write. Finally, there's a bunch of people that have been working pretty diligently, like Simbi that you saw in the previous presentation, working on building tools for robot navigation. So you're not reinventing this wheel either. And basically, this is called the ROS nav stack. And what the nav stack allows you to do is take these complex sensors like your LiDAR, move around an environment, build a map, and then estimate your position from that map. As I've said before, ROS is also all of these simulation tools. And the simulation tools, I think, are really pushing the future of robotics. And the reason that is without simulation, robotics is extremely expensive because you need a robot, and robots have parts, and parts are expensive, and they're tedious. They break, wires come undone, stuff gets stuck. So simulation basically allows you to build a robot without having to worry about any of that. And what's powerful about all of that is that it allows you to build robots that you don't know if they'll work or not. So it allows you to be a little bit more liberal in what you're doing and what you're trying. And we've really pushed on this technology in the past few years. And this is because we've actually started running competitions where you just build a robot in simulation. Generally, simulation requires you have what's called an URDF model. So that's URDF. It stands for Universal Robot Descriptor Format. And basically what you can do is you take your CAD software, you design your robot in CAD, you can export it, and now you have this 3D model that you can then use for simulation. What's cool about simulation is that you're not just simulating the robot and maybe the physics of the robot itself, you can also simulate the sensors, so you can simulate the camera, you can simulate the LiDAR, you can simulate all sorts of other things. And you can also simulate all sorts of dynamics, and I'll show you something in a second. And we've built basically the newest version of Gazebo, which is called Ignition, with all the ability to add plugins and take your code and port it from simulation into your real robot. So I have a video. Is it going to start? I know we were having trouble with video yesterday. Going to start? Maybe? Well, I'll describe what you would have seen. So there's actually multiple competitions going on. A lot of them are in part with the DoD or DARPA. And what we've been working on, the one I think I was going to show you, Sub-T. And so basically the Sub-T challenge is something that's going on with DARPA right now. And the whole idea is how do we build robots that move underground, especially when they don't have GPS. And it's very expensive to get a team and build a robot. So what they've allowed people to do is build their robot in simulation, given a few standard platforms, and they just work on the algorithms. They just work on the control. And people can go and test their control, and they can test it in situations where there might be bright light, no light, smoke, fog, all these different things that you might find in a subterranean environment. And you can actually simulate all of that before you ever go underground. Is this going to change? There we go. All right. So I talked a little bit about what ROS is in terms of software, but the other thing I think people need to keep in mind is that ROS is also a community of people who've been working together to build robots for well over a decade. And so sort of the things that we provide as a community to you if you're building a robot. The first one is the ROS Wiki, which is wiki.ros.org. So this is basically every package maintainer who's built a package for ROS or built a tutorial, they all kind of go here. And it's kind of like Wikipedia for robots. So you can go here, understand like how something was built, how to use it, what the fundamentals that you need to understand about using it are, and you can go here and learn how to use all these different packages. Recently, we've brought up discourse.ros.org, and so this is kind of a replacement for these old listservs where all of the roboticists would go and say like, oh, well here, we're working on this project, or here, I'm looking for somebody to fill this job position, or I want to announce this robotics competition. So if you go to Discourse, you'll see all these things listed out, and you can actually engage with people that are working on different projects. Finally, we have answers.ros.org, and you maybe, if you go look at this, you'll be like, why did they remake Stack Overflow for robots? Well, it actually turns out that we made it at the same time as Stack Overflow, which is, we're not generic software problems. But you can go here and you can find all of these people who've worked on ROS projects. They have a particular error message that might be very unique to their situation, but somebody's helped them solve it. And so we've sort of put all of the knowledge about how to build robots in one place. All right, so you may be asking yourself, what does this have to do with R? So first I want to show you the sort of ROS 1 way of actually interfacing with hardware boards. So by and large, a lot of the robots I see lately are things that are based on Raspberry Pis or other single board computers. So you'll see that more often than not. This guy right here, this is a TurtleBot. So this is sort of our standard learning platform. It's just a Raspberry Pi with another board underneath it. So this is the OpenCR board next to it. OpenCR board is basically an ARM Cortex-M7 processor that we use as a generic board that talks with ROS to handle driving various motors and various sensors. The way this usually works is that people use a tool called ROS Serial, and what ROS Serial allows you to do is take something like the OpenCR or an Arduino, set up your sensors, set up your actuators, and you can create an interface to a ROS topic. You basically have to have a sender and a receiver on your main processor to handle this, but you can learn all about this at ROS Serial on the wiki. Here's another example of something that just came out for ROS 1, and this is just a community member who's like, I'm going to go scratch my own itch. So I don't know if you guys know what an inertial measurement unit is, but it's basically the inner ear for a robot or device. It figures out like what the position is, what the orientation is, probably which way is north. These things can go very, very fast now, like 2,000, 5,000 hertz, and be very accurate. But the ones that are very, very accurate and useful for robotics tend to be very expensive. So we just had a community member, Ken Altneller, and he's like, can I make this expensive $100 board for education for 20 bucks? And he was able to. It's a cool little tool. It's a ARM Cortex M4F processor, and it's doing a whole bunch of processing on board to really, really clean up the IMU signals so he can do really, really precise indoor navigation. So as I said earlier, ROS2 changes a whole lot of things that were sort of not great in ROS1 on the pub sub bus. And the main one is that we sort of collapsed all of the interface layers into this ROS abstraction middleware layer. And that allows you to go into a particular vendor and use their underlying DDS system for being your pub sub bus. What this has allowed us to do is actually bring on more capabilities to run ROS in an RTOS environment and run ROS in an embedded system. And generally speaking, this change has also increased performance, improved security, allowed the system to be more deterministic, all these things that you want in a pub sub bus. So right now in ROS2, the very active area of development is working on micro ROS. So right now, micro ROS is usually in RTOS. Right now, it's primarily NUDX. I've heard people saying that they're working on free RTOS. I haven't seen it myself yet. Plus a DDS system for extremely resource-constrained environments. And you can take the combination of the two and run it on an embedded platform like a smaller ARM chip and build all sorts of cool and interesting stuff. What I think is really, really interesting about this is that I think the future for ROS is having all of this embedded hardware ready to go, that we're slowly building up this hardware ecosystem of components that kind of snap together to go build robots that solve particular tasks. Right now, micro ROS is under heavy development with a few demos starting to emerge. I think this is really going to be accelerated in the next year or two. And what I think is more interesting than ROS1 with that ROS serial example is effectively now you can take an RTOS and have it run and speak ROS natively, and you just sort of plug it into your robot that's already running in a ROS system. I should mention that there's a regular working group pushing on developments for this, and I'm sure they could always use a few more developers. There's a current micro ROS reference implementation, and it's this OLMX open hardware board. It's just an STM32, and it's basically Arduino compatible and Creative Commons, and about 45 bucks. So if you want to get dirty with doing embedded ROS work and ARM, it's fairly accessible. Another little bit that I wanted to sneak in here, and you may have seen it already, is that PX4 Autopilot. People have built basically a micro RTPS interface between the PX4 drone, and what this will allow you to do is take your PX4 system, have it talk over this micro RTPS system, and then talk directly to ROS2. And this is pretty sweet because you can now take this drone, use all of that ROS tooling that we've built for visualization and simulation, and tie it to one of these PX4 drones. So I wanted to show you where things were going. So this is ROS distro by commits. And right here at the very far right is November. And basically where we're at now is that ROS2 development, or ROS1 development is winding down, and we're basically at parity with ROS2 development. So if you're interested in these things, if you're starting a project, ROS2 is definitely where you should be looking. All right, so a couple take-home messages. Now that you guys are ready to go and build a robot. ROS is a set of ready-to-go free and open source packages for robotics. And I like to say that right now robotics frameworks feel like web frameworks in 2014, 2015. Everyone wants to do something interesting, and they're not going to spend a bunch of time reinventing the wheel. The advent of micro ROS plus ROS2 is going to allow us to basically take over the whole robotics stack all the way from the RTOS systems at the hardware level all the way up to the high-level planning systems. And if you're building hardware, ROS support is going to basically bring in a huge community of robot developers already. And the last little bit of advice that I give anyone about robotics, and particularly if they're thinking about building robotic applications, is that generally a robot plus a vertical market is the best chance of success of getting something done. Cool. Well, you guys can get on the road. It's starting to rain out there.